Hi everyone, this section and notes is on logarithmic functions, and it goes along with the last section, which was on exponential functions, growth and decay. They are very much related to one another, so it's good if you do this right after doing exponential functions. Okay, so in the last section, recall that we looked at a basic exponential function where the output equals some kind of base raised to the power of the independent variable x. And of course we realized that there were some conditions in the last investigation on that base and what the resulting output would be. So let's just write down what that looked like. We saw that the base cannot equal 1, otherwise that turns into a linear function, not an exponential function. And we saw that the base had to be greater than 0. If it were a negative number, it did not yield a function at all, let alone an exponential function. And I guess we should say that when we had a base that was greater than 0 but less than 1, we had decay. And if we had a base that was greater than 1, we had growth. I guess we should write that. The output was always positive, so the y is always greater than 0, and not equal to or greater than 0. It has to be greater than 0. And we found that because there was no limitations on the domain. X could be negative, and it could be positive, but we realized that when we looked at very negative numbers, all that means is that the resulting exponential here, b, being raised to that negative power, would just turn that into a very, very small number, 1 over b to that power. And then if b were raised to a very high positive number, it would just be a large growing number. So regardless, as that x gets more and more and more negative, y approaches 0, never touches 0, but nevertheless is always positive. Alright, so if you recall, in the last section of notes, we looked at, just as an example, y equals 2 to the x. There's nothing magical about a base of 2. It was just happened to be the example that we kept looking at. And we just went ahead and we went through and we looked at various negative and positive exponents for that independent variable and what would happen to the output. And we graphed that and we saw we've got this nice exponential growth. And here you can see that the curve is approaching 0, which means that we could say y equals 0, or the x-axis is our horizontal asymptote. And what else can we say? As the exponent grows larger, so does our growth curve. So what if, for instance, well, let me go back here and just say that it's very easy to see that when x equals 0, say, that anything with an exponent of 0 is 1, and 2 to the 1 would just be 2, 2 squared would be 4, 2 cubed would be 8. Very easy to see these numbers on the curve, and simple enough. But what happens if I wanted to see what kind of exponent x would be if I had an output of, say, 5. So if I looked at something here, in other words, I'm saying I want 5. What kind of exponent x is going to give me 5? Well, I guess I can look at this curve here and I could see, well, it's definitely greater than 2. It's less than maybe 2.5. So I can estimate it from the curve. But what do we do if we want absolutely the precise exponent, which is, obviously a decimal? So here we're looking at an output of 5, and we want to know what this corresponding x would be. Well, in order to go in reverse now, we need some kind of mathematical function over here. So we need some kind of mathematical function where we tell it whatever that base is, and we know what that output is, and we want to get back that exponent. So we're looking for something like that. And that mathematical function is called a logarithm. And that's spelled this way, logarithm. And it's been around a long, long time. I think, if my history is correct, a Scottish gentleman named John Napier, actually published a paper in 1614, so it's quite a long time, and probably he published, I don't know this for sure, but probably he published something on this concept that had been in use by others for some time. So I don't think he invented it necessarily, but he documented it in some tables. So the way we write that notationally is we abbreviate logarithm with log, and we use kind of like a sub number here, and that's the placeholder for base. And we're going to apply this mathematical function to the output. And what we get back is the input, the exponent. So we read this as the log of y with base b. That's how we would read that. And in my particular example that I posed here, we would write that as, what is the log of 5 with a base of 2? And I'm asking what the resulting exponent would be. So that's the concept, the basic concept of logarithms. Now, I had a professor at UMass Lowell, I'll give her credit, her name is Dr. Regina Panasuk, and she said over and over and over to students, the log of anything is the exponent. And she recommended that you say that over and over and over again. The log of anything is the exponent. And I think this is some very wise advice. Things are going to get quite complicated, not in this section necessarily, but in your very near future, you're going to be solving log equations that look extremely complex. And if you just remember the log of anything is the exponent, and you have good solid understanding of exponent properties, the two combined will help you break down any complex problem. But this is something that you're going to want to really, really take to heart and say over and over to yourself. Okay, so definition of log, as I had set up here, we take the log of the output with a particular base, and we're going to get back that input or the exponent. And this is true if and only if, and by the way, we've looked at this abbreviation before, IFF, if and only if that output equals that base raised to that independent variable. And as I said in the beginning, up at the top, as well as in the last section of notes on exponential functions, y absolutely, that output is greater than 0, not equal to 0. The base cannot be equal to 1, otherwise that's a linear function, and the base absolutely cannot be negative. Otherwise we yield no exponential function at all. So I always have to put this caveat here. So this is the basic definition of a logarithm, and it's going to take a little while since it looks very new, this notation. It's going to take a little while to understand, but keep looking here at this definition, and I think you'll start to get it. All right, so let's take a look at some examples here. We've got logarithmic form of several equations here. Let's rewrite them into their exponential form. I'm going to go ahead and keep going through how to do each one of these here, but I would recommend you try to do it on your own. Hit the pause button, do it on your own, and then go back and check your answers. Okay, so here I go. So we've got a base here of 10, so I'm going to immediately write my base of 10, and the log of anything is the exponent. The log of anything is the exponent. So here 2 is the exponent, and that equals the output, 100. So 10 squared does equal 100. All right, our base of 3, and the log of anything is the exponent. So 3 to the 4, that equals 81. So this is the exponential form of the equation. Here, the base is 4. The log of anything is the exponent, so 4 to the 0. Any base to a power of 0 equals 1. Our base here is 8, and 8 The exponent is 3, and that equals 512. The base here is 3. The log of anything is the exponent, so 1 is the exponent, and 3 to the 1 is just 3 itself. And here we have a base of 2, and the log of anything is the exponent, so we have 2 to the negative 2, which is the same thing as 1 over 2 squared, which is 1 over 4, which we could say is in decimal form. In decimal form, we could say is 2500ths. Okay, pay special note to a couple of these properties here. If you notice, here is one that's kind of important to look at, and also here is important to look at. Special log values. So if we have the log of 1 here, so in this case log base 4 of 1, the log of 1, it doesn't matter what that base b is, the log of 1 is always going to be 0, because whatever that base is, to a power of 0 is going to equal 1. So that's just a special log value. The log of 1, regardless of the base, is always going to be 0. And then another one here to look at, if you're taking the log of a number, and that number is the same as the base, so in our particular example we had the log of 3 with a base of 3. The log of a particular number, and that's the same base, that's always going to equal 1. Why? Because the base raised to the power of 1 is going to be equal to itself. So those are two special log values that you should become familiar with and easily recognize going forward. All right, some conventions here. We've got a variety of bases. We know our base can't equal 0. We know our base can't equal 1. We know our base cannot be negative. But it can be anything other than that. So there's an infinite number of bases that we can use. However, there is one that is used very, very frequently, so frequently that we call it the common logarithm, and that's a base of 10. So here I have written the log of 1,000 base 10, and that is often written in textbooks and in worksheets where we just drop the 10, the base. So if you see log of 1,000, it's assumed. If you see no base listed there, it is assumed to be base of 10. Now, the base of 10 is, the common logarithm is so popular, it's used in so many real-life scenarios. It's used for the Richter scale in measuring magnitude of earthquakes. It's used on a decibel scale, which measures loudness and sound, also RF power, the same scale as decimals. It's used in a scale on photographic exposure. It's used in thermodynamics on the entropy scale. It's used in a stellar type measurement on how bright a star appears. So that's why it's called common logarithm, because it's used in so many different real-life applications. Now, there's also something called the natural logarithm, and we talked in the last section about the natural base e. Remember, the natural base e is approximately 1.781 ... It's a constant, but it's a constant that's used in all kinds of real-life situations. And when you see the log with a base of e, you will never see it written like this in a textbook. Okay, but the same concept is a log base e, but the way you will always see it written is this ln, and you read that as the natural log of 55. And it is assumed then the natural log of 55 is with this unspoken base e. When you see ln, you know that that unspoken base e is there. Okay, so these two things are something that this notation and this notation is something that you're going to need to memorize and know exactly what it means. All right, so let's evaluate some expressions. These are expressions. They don't have an equal sign, so we can find some kind of number or variable expression to represent them. And again, I would recommend that you try to do those on your own. Hit the pause button right now and try to do it on your own, and then come back and check your answers. In the meantime, I'm going to continue to go through each problem. Okay, we have a base of 4 here, and we're asking ourselves, okay, what exponent with a base of 4 is going to yield 64? So the output, if you will, the result of any log, the log of any number is the exponent. So here you can see that the answer is 3. The exponent here, or the expression log of 64 with a base 4, the answer is 3. All right, the base here is 1/5, and we're asking ourselves, what is that exponent that is going to yield 25? And of course, that exponent is going to be -2. And next one, we have a log of 4 raised to some kind of exponent here. It's a weird exponent. It's a negative decimal type exponent, but it's got a base of 4. So we're taking the log of a base, or sorry, the log of a number that number happens to be the same base. So rewrite that, and we're going to take our base of 4. We're looking for whatever that exponent is that's going to yield this. So when you write it that way, hopefully you can see very simply that that exponent must be that -38/100. So that would be the resulting numerical expression for this here. Okay, log base 3 of 1/27. So we have a base of 3. We're looking for what is that exponent that is going to yield 1/27. And of course, easy to see that that exponent is -3. We've got the natural log of e. So we remember there's an unspoken base here. When you see the natural log, the unspoken base is e. So you have e to some kind of exponent, which is going to lead to e, this output here. And of course, that exponent would be x equals 1. And finally, we have a base of 4. And we want to know what is that exponent that is going to yield an output of 1/4. And easy to see that that exponent is going to be a -1. Okay, so all of these are quite easy to see. We can evaluate these all in our head with no use of a calculator. Very easy to manipulate these numbers around and get what that exponent is. However, just like on the previous page, I was posing the question, what exponent would yield, say, 5 as an output with a base of 2? Well, that's not so easy to do in our head, and in which case we would use the calculator. So let me show you how to evaluate different logarithms using the calculator. I've got 3 different categories here. I've got the common log, which is a base of 10. I've got the natural log, which of course is a base of e. And then we've got any other base that falls within the appropriate range. All right, so let's start with the common log. The common log button is right here on the TI-84 Plus graphing calculator. So it's LOG, capital LOG, and right above it is its inverse operation, which is 10 to the x. So you would, if you wanted to take the log base 10 of something, you would just hit this button. And if you wanted to access the inverse operation, then you would use the blue second key and then hit the log button. So, for example, I put here, evaluate the log of 6. Of course, there's an unspoken 10 here. If you don't see a base there, it's assumed to be the common log. So you would hit the log button on your graphing calculator, input 6, hit return, and you will get, you will get something like this answer here. All right, how about the natural logarithm? The natural logarithm is right below it on the calculator, Ln, capital Ln, and its inverse function is right above it, accessed through the second button, and that inverse operation would, of course, be base e to the x. And so if you wanted to evaluate, say, the natural log of 5, of course we know that the natural log has this invisible base e here, you would just hit the natural log button over here and input 5 and enter, and you will get something like 1 61/100 number. Now, any other base that's not the common base or the natural base, then you would access it, well, I think there's two different ways, but I think the easiest way to access is using this math function button. If you hit the math function button, you will see a huge array of built-in math functions into the calculator, and I think it starts 1 through 10 actually, and then it starts with capital letters. So you're going to use this downward arrow and scroll down, and you're going to find the capital letter A, which you'll see here. It says log base and parentheses. And so when you hit that A and hit enter, then what will come up is log, and you'll see a little box to place the base in, and then another box to put the output in. So you would just input your numbers, and in our particular example that I was talking about, on the previous page here, if we wanted to enter a log base 2 and find out what that is, then the exact number, of course we estimated it looking on the graph on the previous page, but the exact number here for an exponent base 2 to get an output of 5 would be this number here. So in other words, we're saying 2 to the 2.3219 is approximately 5. Okay, so you should spend a little time just becoming aware and familiarize yourself with using the calculator. Okay, let's now investigate the inverse properties of exponential and logarithmic functions. And when I say inverse properties, I really mean inverse operations. So, as you know, inverse operations. Inverse operation to addition is subtraction. Inverse operation of division is multiplication. Inverse operation of squaring is square rooting, and so on and so forth. Why do we use inverse operations? We use inverse operations all the time to solve equations, to basically pull any operations away from an unknown variable and basically isolate that unknown so that we can solve for it. And that's why we use inverse operations. Well, let's investigate here what I'm talking about as it's applied to exponential and logarithmic functions. So we know that if we have an output y and it equals some base to the exponent or to the power of our independent variable, of course we always have these qualifier statements about the base, we know if this is true, then our new mathematical operation here, if we take the log of that output with that base, we can get back the exponent, getting back the exponent. So let's take a look here at just this left side. Okay, I'm going to rewrite it down here. So we've got log of y base b equals the exponent. Now, what if I take both sides of this equation, both sides, and I'm going to make them exponents themselves. I'm going to make them powers to that same base b. So here I've got base b. I'm going to take this here and I'm going to make it an exponent, and I'm going to take the same base b over here and I'm going to make the x the exponent. And I can do that because whatever I do on one side of the equal sign, as long as I do the exact same thing on the other, I have equality. So we end up with this funny looking statement here. And what do you notice? B to the x, well, b to the x is up here. b to the x equals y. And so when you look at this then, if we take the base and we then bring it to a power of the log with the same base, the log of something with that same base, well, they undo each other. They are inverse operations to each other. So we're going to get back just the y. So for example, if I have a base of 3 and then I'm raising it to the log of something with the same base of 3, they undo each other. They are inverse operations, and the only thing I'm going to get back is 9. Now, this is going to take a little while to wrap your head around, but if you become very proficient with this, this is how we can easily solve logarithmic equations going forward. So hopefully this makes some kind of sense to you. All right, now I'm going to go ahead and just look at actually I'm going to get rid of this arrow here. Now I'm going to look at just this side of the equation. Output equals some kind of base raised to the independent variable. So I'm rewriting it over here. Now, I would like to take the log of both sides with that same base b. And I can do anything I want to do on one side of the equal sign as long as I do exactly the same thing on the other. So I'm going to go ahead and I'm taking the log base b of y here, and then I'm going to take the log base b of b to the x. Well, log base b of y right here, what do you notice? The log base b of y equals x. So I can replace that with x, and what do I see? I see that when I take the log of log base b of this same exponential here, with the same base raised to the x, that log base b of that exponential, they undo each other. They are inverse operations. So all I get back is x. They undo each other. It's kind of like the same thing as taking the square root of 2 and then squaring it. You get back the 2. They undo each other. And that's exactly what we're doing here. So if we look at a specific example, if I take the log base 2 of something here, now this looks a little funny. This does not look like the same bases here. But we can rewrite this. I could rewrite log base 2, and 4 to the 2x is the same thing as 2 to the 4x. 2 squared times 2x is 2 to the 4x. So here I have the same base with the same base here, an exponential, and they undo each other. So if I were to evaluate this, this simplifies to 4x. Okay, that is a little bit tricky, but hopefully with a little practice we could get used to this concept. All right, now we just talked about inverse properties or inverse operations of exponential and logarithmic functions. Now let's look at inverse functions of exponential and logarithmic functions. And if you recall, an inverse function is when we switch the position of the x and y in a function and then go ahead and resolve for y. Alright, so far let's take a look at what we know. We know that we have an exponential function here. The output equals some base raised to the independent variable. And we know then that our new function that we've been looking at is if we take the log of that output with the same base, we're going to get back that exponent. Now if we kind of reverse, we look at the inverse the inverse function, we're going to move the y over, the x where the y is and the y where the x is. And so we have x equals that base now to the dependent variable. And if we look over here at that, if that's true, and we look at the associated logarithmic function of that, we would say that the log base b of that output is going to give us back the exponent. In this case, it's the dependent variable y. So we consider these inverse functions of each other. Inverse functions of each other. Now, what does that look like in functional notation? Well, we've learned that we can look at that output here, y, as a function notation. It's a function of the independent variable. So we just replace that y here with f of x. That's how we read that. f of x. So we have f of x equals that base raised to the independent variable, and that's the exponent, the independent variable in this case. In all the cases we've looked at so far, that x has been the independent variable, and the output here is the result of that exponential. Now, if we look in functional notation of the inverse function, we have here x equals b to the y, and that inverse function we represent here with this f of x to the a superpower here of -1, and that's just a notation saying that this is the inverse function of f of x. Sometimes you may see this written as g of x. I don't like that. I find too many variables confusing, and I think it's much cleaner to use this it's not an exponent, but it's a notation style to say that this is the inverse function of f of x. And the inverse function then would be this log of x with a base b. So these are inverse functions to each other, and you could see in this case the dependent variable y is the exponent. So they're almost reverse in that way. What do they look like when they're graphed? Well, I'm going to go back to the same example that I've been using all along. F of x equals 2 to the x, and again, that's just y equals 2 to the x. So we've got the same base 2 that we've been looking at, and we know exactly what some of those points are because we've made a table. We know that as that exponent x gets more and more negative, we approach that horizontal asymptote of 0, and we know that 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, etc. And we plotted these and graphed this same function over and over. Okay, so we've got our function here. We've got f of x equals 2 to the x. And how do we find the inverse function? Well, to find the inverse function, we are going to replace the x and y. I'm just going to go ahead and make this y equals 2 to the x. So we're going to replace this as x equals 2 to the y. All right, that's the step we're taking to find the inverse. Now we need to solve for y. Now, how do we solve for y? Y is over here, it's up here in the exponent. Well, how do we undo an exponential function? We undo an exponential function with its inverse operation, which is a logarithmic function of the same base. So I am going to use that same base 2, and I'm going to take the log of base 2 of both sides of this equation, log base 2, and then I'm taking the log base 2 of this exponential, 2 to the y. So over here, everything's fine. I still have log base 2x. And of course, here, if I'm going to take the log base 2 of an exponential of base 2, they are inverse operations of each other. They undo each other. So I just have y over here. And I'm going to go ahead and just rewrite that this way, just to switch it around. And if we wanted to write that in functional notation, we would say the inverse function is equal to log base 2 of x. And it's probably easier to visualize this. We're saying that, let's actually rewrite it as an exponential then. We're saying the base of 2 here to some kind of exponent. Now remember, the log of anything is the exponent. So exponent here is that output y now. The log of anything is the exponent. So we're saying this base of 2 to some kind of exponent is equal to the output. And this looks a little bit different from what we've been looking at so far. We've been looking at the exponent being the independent variable, and now we're looking at the exponent being the dependent variable. So probably the easiest thing to do to visualize this is to again create a table of some points here. So we have x, and x equals our base of 2 to that dependent variable y, and we have y. So normally we would pick some values for our independent variable and we would calculate the dependent, the output. But in this case, it's probably easier to go in reverse. So let's just pick some values for that exponent y and go back and calculate the independent variable. So let's say some easy values for y. Of course, always 0 is a good one. So we could say 2 to the 0. 2 to the 0 would give us an x equal 1. And let's just kind of make a table here. Okay, how about y equals 1? 2 to the 1 equals 2. Y equals 2, we got 2 squared, which is 4, etc., etc. Oops, I've got a little mistake here. This is 2 cubed. Okay, let's go with some negative exponents. Negative 1, we've got 2 to the negative 1 is 1 over 2, which is 1/2. And we'll look at an exponent of negative 2. That would be 2 to the negative 2, which would be 1 over 2 squared, which would be 1/4. So hopefully you can see that as these exponents y become more and more negative, we're approaching an x value of 0. And as the exponent becomes more and more positive, of course, we have the x growing exponentially. So what does that curve then look like? We have some points here. Let's start with x equals 1, and x equals 1 has a y of 0. And we have x equals 2, and that's an output of 1. And we have x equals 4, which is a y of 2, x equals 8, which is a y of 3. And then on the negative side here, if we looked at a very small number of a quarter, we're all the way down here at negative 2. And if we look at an x of 1/2, we're at negative 1. Okay, so this would be what the curve looks like for the inverse function. And I've got a line here. It's actually y equals x. This line goes through the origin with a slope of 1. And you can see that that line is actually a mirror line. It's a line of reflection for these two functions that are inverses of each other. Now this inverse function, again, if we're going to take the log here of a number, we could see that the domain then for this inverse function, x cannot equal 0. In fact, x has to be positive, so we see that clearly in our curve. So x equals 0 here, and that would be the y-axis, x equals 0. This axis here would be a vertical asymptote to this inverse function. In other words, as that exponent y becomes more and more negative, we're going to approach that axis or that line, but we will never touch it. So that will be a vertical asymptote for that inverse function, whereas the original function, 2 to the x, the original exponential function, it has a horizontal asymptote of y equals 0, or the x-axis. So hopefully you can kind of see that that symmetry, if you will. All right, and let's take some practice finding the inverse functions. That means replacing the y with the x and the x with the y, and then resolving for y using our new inverse operations. Now again, I would encourage you to hit the pause button and try to do these things on your own, and then go back and check your answers. But I'm going to keep going and show you how to do each one. Okay, so for this first one, I'm going to replace my y with x and my x with y. And I need to now solve for y. And y is now, we're taking the log of y with a base of 9. How do I undo the log of y? Well, I have to undo log with exponential function. So I'm going to put both of these, both sides of the equal sign in an exponential function. So I'm going to use that same base 9 and bring 9 to the x. And I'm going to, I'm going to use the same base 9, and I'm going to put this whole thing here as an exponent. Now I've got 9 of x. I'm going to scooch over here. 9 raised to the power of x. And of course, the base of 9 here raised to the log of base 9. They're inverse operations of each other. And so I just have y over here. And so my answer is y equals 9 to the x. This would be my inverse function, and if you wanted to write that in function notation, you could say something like this. Number 2, y equals the natural log of 6x. And again, we're going to put x where y is, and y where x is. Okay. Remember, the natural log has that invisible base e. How do we undo or free up that y? We're going to solve for y. We undo that natural log with an exponential base e. So I'm going to use e to the x. I'm going to do whatever I do on one side, I do on the other. And I think it maybe just helps when we're beginners. I'm going to keep showing that natural log with a base of e. And I have e to the x, and of course base e here raised to the natural log base e here, inverse operations of each other. So I have just 6y over here. Solve for y, divide both sides by 6. And I have y equals, and I'm just going to rewrite it, I think 1/6 times e to the x. So this would be my inverse function, and I could write that in functional notation if I wanted to. Number 3, y equals log 2 of the sum of x and 1. Replace y with x and x with y. And I have y stuck inside this log base 2, and so I undo that log base 2 with an exponential base using the base of 2. So I'm going to say 2 to the x equals 2, and this whole thing then becomes a power. So I have 2 to the x, and inverse operations over here. 2 raised to the log of base of 2 undo each other. So I just have y plus 1 over here left, and I'm going to subtract 1 from both sides. And I have y equals 2 to the power of x minus 1. And that would be my inverse function. Number 4, y equals log base of a half of x. I'm going to replace y with x, and I'm going to replace x with y. How do I undo log base 1/2? I'm going to use a half as a base. So I'm going to put 1/2 exponential here raised to x. And over here I'm going to do the same. I got a base of 1/2, and I'm going to raise it to the log base 1/2 of y. So I have 1/2 raised to the x, and this base of 1/2 raised to log base 1/2, inverse operation. They undo each other, so I have y equals 1/2 to the base of x. You could just as easily write that, I think, as a decimal, and that would be my inverse function. Number 5, y equals the natural log of the difference between x and 1. Replace y with x, and replace x with y. How do I free up? Remember this natural log, it's got a base of e. I undo that natural log base e with an exponential base e. So I'm going to do e to the x equals e to the natural log base e, y minus 1. I have e to the x equals, and this base raised to the natural log of e undoes each other. Inverse operation, and I'm going to finally isolate y by adding 1 to each side, and I have y equals e to the x plus 1, and this would be my inverse function. And finally, number 6, y equals log base 7 of 49 raised to the x power. So we're going to replace y with x and x with y. Now at this point, hopefully you see that this right side here can be simplified a little bit. So let's take a look at that. We've got log base 7. 49 is 7 squared. So power on power, we could replace that 49 to the exponent of y with 7 to the exponent of 2y. Now remember our special properties of logs. This is a log of a number which happens to be the same as the base. So we could simplify this right away. In fact, it actually turns out to be linear. The log base 7 of an exponential of 7, that's already an inverse operation right there. So this actually simplifies to x equals 2y. And if I solve for y, then y equals x divided by 2. So this happens to be the inverse function of y equals log base 749. And let's just rewrite this one here so you could see how this original function is written in a simplified form. This is y equals log base 7 to the 7 2x. So this is y equals 2x. Hopefully you could see here, I'm going to rewrite this just to avoid any kind of confusion. This is the original function f of x. It's linear when you simplify it. And the inverse operation here, inverse function is x divided by 2. These are inverse functions of each other, and they're linear. Okay, let's move on by practicing some graphing of logarithmic functions. Okay, so we have a function y equals log of the difference of x and 2, and since we don't see a base written there, we know that that base is the common base 10. Alright, immediately you want to start thinking about domain and asymptotes. We can't take the log of anything that's not positive. It has to be positive, and it cannot equal 0. So immediately you want to start thinking x minus 2 cannot equal 0. So what does that mean? That means x cannot equal positive 2. Right away you know x equals positive 2. That's going to be a vertical asymptote. Our curve is not going to touch that line. Also, we know x minus 2, it has to be positive, so x has got to be greater than 2. So right away, we know our curve, our graph is going to be over here. It's not going to touch x equals 2, and it's got to have values of x greater than 2. Okay, let's go ahead and rewrite our logarithmic function here, more in exponential format. So what we have here is a base of 10, and I don't like the look of that. That almost looks like a b. The base of 10, and the log of anything is the exponent, so y is our exponent here, and that equals x minus 2. And let's go ahead and solve for x. Might be easier. So we have x equals 10 to the y plus 2. So let's go ahead and make a table of values. We have x, and we have x equal to 10y plus 2, and we have some y values. And again, we're going to kind of treat the y, which is normally our output or a dependent variable, we're going to kind of treat that as the input and go in reverse and calculate what x, which is normally our input variable. It's just easier in this case to pick some values for y and then solve for x, since this dependent variable is actually the exponent. So let's pick some natural numbers. Let's say 0 is always a good one first. So we've got 10 to the 0 plus 2, 10 to, well, any base 2 in exponent 0 is 1, 1 plus 2 is 3. And looking at y equals 1, we've got 10 to the 1 plus 2, well that would be 10 plus 2, which is 12. 2, well you can see the numbers really growing fast. Whoops. I've got 10 squared, which is 100, plus 2 is 102. Now let's look at some negative values. So I've got 10 to the negative 1 plus 2. That's 1/10 plus 2. And so we could simplify that to 2 and 1/10. And likewise, 10 to the negative 2 is 100th. So that would be 2 and 100th. Okay, so you could see what's happening here with this vertical asymptote. If we just go a hair over 2 on the x-axis, 2 and 100th, we are down here at y equals negative 2 and 2 and 1/10. Very hard on the scale to graph this with any kind of accuracy, but you could see what's happening here. And x equals 3, that would be our x-intercept. And 12, well, I just barely have that on my graph, and of course 102 is way off my graph. So you could see what's happening here with my vertical asymptote, and my graph is coming over here and up and away it goes. As x approaches to the range of the y, becomes more and more negative. Okay, so what does that mean in terms of the domain and range? Well, the domain here is x, everything greater than 2 is fine, and the range, there's really nothing limiting the range, so the range is y equals all real numbers. And you would say, of course, that x equals 2 is a vertical asymptote. Okay, I have a couple more examples here. I encourage you to hit the pause button again and try to do these on your own, but I'll continue and show you the full solution so that you can check your answers. Okay, so we have a function y equals log base 2 of x plus 1, and what we're going to do here is go ahead and get rid of this negative 1, or sorry, this positive 1 here, and get that over here. So we've got y minus 1 equals the log base 2 of x. And the log of anything is the exponent, so we're going to rewrite this logarithmic function more in exponential form. So we've got this base 2, and it's raised to y minus 1, and that is going to equal x. Again, we have sort of our inputs and outputs awkwardly reversed, but let's go ahead and start thinking about asymptotes first before we make a table. So we see we're taking the log of x here, so x certainly cannot equal 1, or sorry, it cannot equal 0, and it has to be positive. Okay, so right here you should realize immediately that x equals 0, which is the y-axis, is our vertical asymptote, and our graph is going to be over here to the right. in values x greater than 0. Alright, so let's create a table. We have x equals 2 to the y minus 1, and we have some y values. Again, we're going to treat the y kind of like an input, just makes our life easier. Okay, so let's pick a nice value like 0. We've got 2 to the 0 minus 1. That's all up in the exponent. So that would be 2 to the negative 1, which is 1/2, 1 over 2. And y equals 1, that would be 2 to the 1 minus 1. That's 2 to the 0. Anything to the 0 exponent is 1. And we have 2 to the 2 minus 1. That's 2 to the 1, which is 2. And 2 to the 3 minus 1, that would be 2 squared, which would be 4. We might as well get one more in here about y equals 4. That would be 2 to the 4 minus 1. That would be 2 cubed, which is 8. And let's try some negative numbers. We've got 2 to the negative 1 minus 1. That's 2 to the negative 2, which is 1/4. And one more. We'll do 2 minus 2. That would be 2 to the exponent of negative 3, which would be 1/8. Okay, so we know, we've already said that the y-axis here, x equals 0, is going to be a vertical asymptote. We could see at a very, very small value of x, we're at negative 2 here. 1/4, very tough to graph this with accuracy. And we go up to 1/2, and that is our x-intercept. And 1, 1, 2, 2. And we've got 4, 3. And I might as well go all the way out to 8, 4. So we've got this asymptote here, the axis, and we'll be growing in that direction. So our domain then, you can see, is x is greater than 0. Our range is all real numbers. And we've got x equals 0 as a vertical asymptote. Okay, last graph, y equals natural log of x minus 1. I am going to use the inverse operation of plus 1 here. I've got y plus 1 equals the natural log of x. We want to rewrite this in exponential format. And remember natural log, invisible base e, natural base e. And so the log of anything is the exponent, so we've got our base e to the exponent of y plus 1, and that is going to equal x. Okay, at this point we want to start thinking about the domain, so you can see that x cannot equal 0, and x has to be positive. So our y-axis here is going to be our vertical asymptote. And let's look at this in terms of an exponential. So we have a base of e, and the log of anything is the exponent, so we have e to the y plus 1 equals x. So we're going to set up a table. X equals e to the y plus 1. And we're going to, again, look at things a little bit backwards. So picking some values, y, we have e to the 0 plus 1 would be e to the 1, which should just be e. Y equal 1, we've got e to the 1 plus 1, which is e squared, and y equal 2 would be e2 plus 1, which is e cubed. Taking a look at some negative values for that exponent, we have e to the negative 1 plus 1, which is e to the 0, which is 1. And then negative 2, we would have e to the negative 2 plus 1, which is e to the negative 1, which would just be 1 over e. And we can approximate these values using our calculator. We can use a decimal approximation. Since I guess our scale over here is very small, we might as well just go to the 10th, I would say. So e is approximately 2.7, and e squared would be approximately 7 4/10. E cubed is approximately 20. We've got 1, and 1 over e is, I guess, about 4/10. So we can graph x equals 4/10. We would be down here at a y of negative 2. X equals 1 would be at negative 1. And x equals e, or 2.7, approximately here, is our e is our x-intercept. And over here at 7 4/10, we would be up at 1. And then x equals 20, we would be off the chart. So you can see our curve is kind of going like this. And our domain then would be x has got to be greater than 0. Our range, y. Again, there's nothing limiting the y values, so that would be all real numbers. And our x equals 0, or the y-axis, is going to be our vertical asymptote. Okay, so this section was long, and there's a lot of concepts in this section. With a little practice and just rewriting logarithmic functions in their exponential format, using those inverse operations, and just really applying properties of exponents, I think you'll be able to get the hang of it. Hope this helps.